Okay, folks, we have arrived to state preparation and measurement. In this section, you will learn about errors caused by the measurement in the measurement apparatus, typically because the measurement apparatus doesn't fully function as we want to. State preparation is something we'll leave to the bonus content section in the interest of time. Let's return to our 1-qubit example where we now have some generic unitary, it can be whatever, our quantum Fourier transform algorithm or really anything else. Then we have a meter that measures 0, 1, cat is dead or alive, and it follows the following rule that we already know about. Something special will now happen. We won't get M directly. Instead, our measurement apparatus might look a little bit more like this, rusty old ruler rather than our clean, nice, beautiful first apparatus. Maybe the apparatus is having a bad day and it's having a little trouble reporting our right answer. So what that means is that with some probability, we'll have an error in the measurement. Let's go to our cheat sheet and write this out. The outcome of our measurement over here is going to be M, a classical random variable. And this time we're going to denote it as the ideal outcome because we're going to have a noisy outcome in a second. So to that end, we're going to pick up here the, well, I guess we'll draw it out manually. How about that? We're going to say that M has two possible outcomes, the outcomes 0 and 1. And that's the sender, if you want, ideal or sender. That's what our apparatus wants to tell us. However, it's dusty and muddy and rusty. And so what we're actually going to measure will be another variable. We'll call it M tilde to denote that it's our noisy measurement outcome. And it will be related to M. It can also have the values 0 and 1, but with some error probability, things will get flipped. So let's say that with probability 1 minus epsilon, when M is 0, we get M tilde being 0. In other words, the error of measuring 1 when really we should have measured 0 will be epsilon. If you want, I can write that also as the following way, to say that the probability to get M tilde equals to 1 when M is equal to 0 is equal to epsilon. And that's our, that's an error, that's a confusion. Similarly, the conditional probability, P, to measure M tilde is equal to 0, given that M is equal to 1, is just 1 minus epsilon. Similarly, we can have the converse, which is that suppose M was meant to be 1. However, with some error probability, let's pick the letter nu, we're going to instead measure 0. And so with probability 1 minus nu, our measurement will be correct. So I can write these out as well, that with probability P, M tilde is equal to 0 when M was 0, M tilde is equal to 0 when M should have been 1, was 1, is equal to nu. And so the probability that M tilde is equal to 1 correctly when M is equal to 1 is equal to 1 minus nu. And you can see that this picture has some very symmetric relationship. Essentially at this stage, everything is going to be classical post-processing, so we won't dwell very long on this. Now, because we're working with transformations of all of these probabilities, the probability that M is 0, the probability that M is 1, and so on, let's introduce a way to organize the information. So on the left here, let me summarize P, M as a vector. of the probability that m is equal to 0 and the probability that m is equal to 1, which I can write as 1 minus p and p. And then on the right hand side here, I'll introduce the vector, the probability vector pm tilde, which is equal to the probability that m tilde is equal to 0 and the probability that m tilde is equal to 1, which is going to be just let's say 1 minus p tilde and p tilde, where p tilde is the noisy probability to measure 1. So p tilde is noisy probability. Okay, great. Excellent. So how can we understand the actual probability? In other words, what is the probability p that m tilde is going to be 0? With what probability will we get 0? Well, clearly we can get 0 two different ways, that m was 0 or m was 1, both of which can lead to m tilde being 0. Based on these conditional cross probabilities. So you can just follow the arrows up here. So let's do that. So this is simply we can write this as the sum that m tilde is equal to 0 given that m is little m, where m is in the sum of all possible values it could take, which for this expression is just the probability that m tilde is equal to 0 given that m was 0 times the probability that m was equal to 0 plus the probability that m tilde is again equal to 0 conditioned on m being 1 times the probability that m is 1. Okay, and similarly you can write the exact same thing for the case where we want to know that m tilde is equal to 1. It's the same expression, simply swapping out the first argument in the conditional probability. Everything else will remain just the same. Okay. And m is equal to 1. There's the probability that m is equal to 1. Okay, so let's highlight the only difference here between the two, which is really what we condition on at the end here. That's the only difference. You might already notice that we can simplify both of these expressions pretty easily and nicely. Really, on the left hand side here, what we have is this vector expression. And on the right hand side here, notice that we're multiplying by the exact same elements or vectors expressions of this here. So we can take that expression and write out the total probability vector that m tilde takes some particular value, which I can write like this: p of m equals tilde equals to 0, p of m tilde equals to 1. Remember, m tilde is the noisy variable, is simply some matrix, which I'll call A, times the probability vector p sub m of the original vector. So this is some matrix A times the probability that m is equal to 0 and p times the probability that m is equal to 1. And you can deduce this out pretty easily, that this A matrix is just equal to those 4 terms that you see over here. And in fact, it's easy enough for me to try to copy this, simply paste it here, delete the entries here, and form our M matrix this way. Sorry, A matrix this way. So this is the A matrix. You notice that it's containing the conditional probabilities. The first column corresponds to the case that m equals 0. Notice here. The second column corresponds to the case that m equals 1. The first row here corresponds to the case that m tilde, the output that we actually measure, is 0, or that the output we actually measure is 1. Okay, so that's what the A matrix tells us. And we can summarize that noise A matrix as 1 minus epsilon, and nu, and 1 minus nu from the numbers above. Excellent. Now, notice that if there is no error, nu is equal to epsilon is equal to 0, and it follows that the A matrix is simply the identity matrix, or its diagonal identity matrix. In other words, in the ideal case, the A matrix doesn't do anything. It doesn't transform our probabilities to measure the correct outcome in any way. It keeps them the same. So that's the ideal case. On the other hand, if we do have some noise probability, you notice that the A matrix has a particular form. It's known as a stochastic matrix, where I'll point out that the sum on any row, on any column, excuse me, is equal to 1. Okay, you notice that this here sums to 1, and this column here will sum to 1. So, in other words, this A matrix contains all the information we need to know and we need to have about the error that we're going to find in our measurement between what we actually should have obtained, let's say on the sender side, and what we actually did obtain, which is on the outcome side. Okay, so in fact maybe one way to draw it is a bit like this. Hopefully not too many arrows at this stage. Excellent. Okay, so what does that mean for the probability that we will try to estimate? In other words, if I look at the noisy probability, p tilde, which, if you remember, is the probability that m tilde is equal to 1, which is the noisy outcome that we only have access to, that's going to equal the probability that m tilde is equal to 1, given that m is 0, times the probability that m is 0, plus the probability that m tilde is equal to 1, given that m is 1, which is the correct situation, times the probability that m is 1, which is nothing other than epsilon times 1 minus p plus 1 minus nu times p. And if you simplify this, we're going to find that this is p plus epsilon minus nu plus epsilon times p. So, great. Let's actually rearrange these terms a little bit in the following way to understand what this means. So remember that if there is no error, then epsilon is 0. So in other words, both of these terms are 0. Perfect. Then p tilde equals p. That's the ideal case. If you have an error, the error can do two things. If you have an epsilon, which means that you have an error to go from 0 to 1, you are going to have an offset in your probability. If you have either an epsilon or a nu, basically any error, you're also going to have an overall shift in your error that will depend on p. And that looks like this. In an experiment, what you're going to want to do is understand how a measurement error, so in some way you'll be able to characterize nu and epsilon, will actually bias your estimate of your quantum Hamiltonian or whatever observable you're trying to estimate, and how it will both shift the range and offset it. Because if you can do that, you can also undo its effect. And we'll touch on that in bonus content. Here, let's just visualize the effect. On the x-axis here, we have the ideal probability to measure 1, p, determined by our quantum algorithm. On the y-axis, we instead have the probability p that we're going to experimentally find due to the scrambling and the noisy measurement. So if you want, I can write ideal here and noisy here. Let's take a few examples here. First is the ideal case for an ideal apparatus, where epsilon is 0 and nu is 0. And that's exactly what this gray curve here will give you. It's just the y equals x line of slope 1. So it tells us that when we have a quantum state that is prepared in the 1 state, we'll expect m equals 1 and we'll measure exactly p tilde of 1, and likewise for the ground state 0. However, suppose we now have some error, which I'll call, in this example, an epsilon of 0.08, so 8% error probability to go 0 to 1, and a nu of 20% probability to go from 1 to 0. What happens then? Well, we can see that unfortunately, first of all, even if we prepare the state 0, if we prepare the ground state 0, we're never going to measure a probability p tilde of 0. Instead, we're going to measure a probability p tilde of epsilon. Similarly, if we prepare the 1 state, in the noisy case, we're going to measure a probability not 1 ever of the coin flip. Instead, that's going to be reduced, and instead it's going to be, and we can kind of write it out here, it's going to be 1 minus nu. So that will be the upper bound. And clearly there's a big difference here of nu between the ideal and expected. So notice on the upper side we have nu, and on the lower side we have epsilon. And obviously the difference highlighted in red here between the gray curve and the red curve is going to be the actual error of the measurement. So let's write that in explicitly. And let's make sure we've specified that this is the noisy curve. Great. The span, the total span that's left, which you notice is diminishing as we go along, since on the bottom here we have a bound of, let's put it in, we have a bound of epsilon and nu on the top. The total span that our measurement can now span is smaller than what we had before, and in this case it's really just limited to 1 minus the two errors, 1 minus nu minus epsilon. That span is known as a metric that you often see. It's known as the fidelity, assignment fidelity, or twice the assignment fidelity. I write this little symbol here to indicate that this is a definition. There's different definitions for the assignment fidelity, so you have to be a little careful, but that's the normal one, and that's the one we'll consistently use throughout the course in a lot of our papers and nomenclature. Notice that any point you pick, except for one very special point on this entire curve, means that you get a wrong answer. So for instance, if I pick the value, if I pick the values 0.6 for my ideal expectation, that's going to, by this curve and errors, turn into a different, unfortunately for us, value that we're going to obtain and measure, and that's, in this case, it's going to be around 0.5. So you have to be careful when you have measurement error, which is unavoidable. You will have it, typically a few percent. Here I've shown a much worse case error than what you see in real experiments, and you have to correct for this. In the bonus section, we'll talk about how you can take this A matrix and you can actually invert the action of the noise and completely undo it. Let's return to our favorite example of a qubit with the qubit flipper algorithm that we had started out earlier. Now in this particular example, remember we repeated a noisy gate d times and looked at what the evolution. This time we're going to keep the noise of 3% coherent error, since we determined that's what we see in the experiment. We're going to also now add in a readout error, which in this case I'm going to estimate is about 2% here and about 5%. So these are the probabilities. Remember that an ideal 0 goes to 1, that's epsilon, which will be 2%, and an ideal 1 goes to a noisy 0, and that's going to be 5%. What does this do in our experiment, in our data? Well, just as we saw on the curve a second ago, notice that the range in our notice that the range of our graph, which should have been +1 to -1, is now diminished and depleted. On the top here, when we should have received a 1, we now received something smaller than a 1. So you can associate that with this expectation value epsilon. And on the bottom here, you can associate that with this expectation, not epsilon, but nu. The span here is twice that of 0 to 1, since we're looking at the z observable instead of the 0 to 1 observable. It's simply a scale and shift. So you're going to have some factors of 2. But overall, the readout error will immediately explain what's happening here at the very beginning, as well as what's happening here on the limitation at the bottom, and why this value does not exactly line up with ±1. You'll also notice, if you look carefully, that overall the center of this oscillation is slightly shifted from 0. And that's again explained by both of these noisy parameters. Awesome. So I hope that you'll retain that. If you see that in your data, you're going to know that you have readout error to take care of if you see these shifts or offsets and biases in your expectation values. Let's get to some questions. So answer these, light up the chat. What do you think the answer to the following is? Question 1 is about readout error. What is it due to? A, B, and C will look very similar to what you saw before in the previous section with projection noise, but I'll give you a hint, the answer is not the same. So what can you do to reduce readout error bias? Increase the number of samples, you cannot undo it, or apply readout error mitigation. All right, let's give you 5 more seconds to answer in the chat, A, B, C. Okay, so the answers are, readout error is due to, it's not classical limitations, it's not quantum physics like it was for projection noise. This time it's really the inefficiency in the measurement apparatus. It's some error or inefficiency in the measurement apparatus, which can in principle be undone or fixed. 2, to reduce readout error bias, what can you do? Well, yes, you actually can undo it. Increasing the number of samples will not help in this case. So that doesn't work. That only reduces projection noise. Very important distinction. The only thing you can really do is to apply readout error mitigation, which we touch on in the bonus section. I'm so excited. On our journey along noise, we've covered coherent noise, projection theory, and measurement theory and projection noise. Also, we covered a part of spam measurement noise, and now we finally made it to the quintessential quantum noise, which is incoherent noise. And this is going to drive and dictate so much of what you will see in real lab and in experiments. It's really the true limitation to modern day quantum experiments. It's what really quantum error correction is meant to fight and tackle. We can only begin to explore the land of incoherent noise, which can lead to quantum trajectories and many other fascinating topics in physics. But let's start with a review and an experiment of what does it mean to be incoherent. So imagine a box. This box can have 1 or 2 states. Each time you reach in this box, it's a magical box, don't ask me why. Each time you reach in this box, you get 1 of 2 quantum states, either psi1 or psi2. You don't know which one you're going to get. You're only knowledge about this box is that you're either going to get psi1 or psi2 with some probability. Let's just label them with probability p1, you get psi1. With probability p2, you get psi2. Because each time you get a state, we can say that the two probabilities sum to 1. It's not too important for our discussion, but let's just put that in. So how do we now handle the questions such as, suppose over all this ensembles I want to ask, what is the expectation value of some observable, let's call it a hat, given that I don't know which state I'm actually going to execute this on? Well, let's think back to what this means. If you had a single state, you could take psi and take the overlap with A. The trick here is to realize that this expression is just another way of writing an inner product, or a, if you want, an overlap of some sense. Really, this is the overlap between the state psi written like this as a projector. It's the projection operator. It's the operator that says how much am I on the state psi, overlap with A. That may look a little complicated with this comma. Notice that there's a comma here. This is not direct notation. This is inner product notation in mathematics. The way you would write it in quantum typically is with this operation known as a trace, where you'd write that this is equal to the trace of psi acted on A. To remind ourselves what the trace of an observable A is, this is just the sum. It's the sum of the diagonals, if you want, of that observable. In some basis, let's call it n, we simply sum all of the diagonal elements, and the value is trace independent, is basis independent. So no matter what basis n you choose here, you're always going to get the same value of A. Okay, this is true here for pure states, but let's keep chugging along at this. Suppose now that in one case I'm going to measure A with respect to psi1, which will look like psi1 A hat psi1, with some probability p1, which I can write as the inner product of psi1 with A, and also I can now write that the expectation value of A, if I had the second state, which I don't know whether I do or don't, but that will happen with some probability P2, will similarly just be the expectation value of psi2 with A hat. Hopefully you can read my handwriting here. Great. So, as any good physicist, you realize that what now happens is that when we want to indiscriminately find the expectation value of A, and hence this little person here is yelling, the average value of A is going to be of the weighted combination of these two. It's simply the probability of measuring the expectation of value of A given psi1 plus the probability of measuring the expectation value of A given psi2, which is just the classical combination of these two things. This expectation value, both of these are just classical real numbers. The trick here is to realize that, again, this expectation value is just a classical, is just a linear functional. So we can put the P inside of the expectation value, just like we did earlier in our lecture. And now we can rewrite this again using the notation that we had up above, where I can use now the fact that we can write that as an inner product. So this is going to be psi1 psi1 multiplied by p1 inner product with A plus p2 psi2 inner product with A. Because the inner product is linear in the first argument, when the first argument is permission, which these are, then we can simply write this as the inner product of p1 psi1 plus P2, psi2, psi2 with A. And this is exactly going to indiscriminately average over all the different possible states, psi1 or psi2, that we can have in our ensemble. In fact, if you look at this and you look at the first argument in this expression, you can think of that as the quantum state of the indiscriminate system. And we denote that by rho, known as the density matrix, or more precisely as a mixed state. It's simply the probability weighted sum of the projectors on all the possible states that you can have. So rho here, which itself is an operator, but we don't usually write the hat on it, is going to symbolize that we can have either psi1 with probability p1 or psi2 with probability p2. From there, all of the usual questions you could ask follow almost in the same way, where instead of using this slightly simpler notation up here, we're going to use this inner product notation, and we typically relate it to the trace operation. So that's going to be our quantum state of a mixed system. And the reason we need to bring this up is because incoherent noise will lead to precisely these kind of states that are mixed, because incoherent noise has to do with the loss of coherence, which has to do with the loss of information. In other words, we no longer know whether we have psi1 or we have psi2. We just know that we can have some probability of having psi1 and psi2 together. Let's illustrate this on a simple toy model example. Back to our favorite qubit, which is now subjected to some unitary operation u1 on this state. How do unitaries act on a particular state when we have a mixed state? Let's have a reminder. Let's say, what is rho at this time? If we initialize the zero state, we can say that rho at the zero time is just the state 0, 0. Whoops, I'm not sure what happened there. After the first gate, remember that the way gates act, if I have a u, that u will transform a psi such as this. If I want to now understand what this looks like, I can call this whole thing some psi prime. And so psi prime dagger, which is the bra version of this, is just psi dagger, which is going to equal to, remember that, A times B dagger is equal to B dagger times A dagger. This is conjugate transpose. So we'll have, if we plug in U and psi in here, and we dagger them, this is going to give us psi dagger U dagger. So this will give us bra psi times U dagger. Now, because U is a unitary, we could simplify this further, but let's just leave it here as it is. So on the right hand side here, the state, which let's say this was rho 0 at time 0, let's say the state after the first application rho is therefore going to be psi prime, which we can now write as U 0, 0 U dagger, applied like this. Excellent. So in other words, our calligraphic U, if I wanted to summarize here, to introduce this notation, since we're switching things up a bit, is going to, so our calligraphic U, which I'll try to denote like this, acting on rho, is going to really be the regular U times rho times U dagger. And that's going to transform our state. Excellent. So that's just a reminder of how the notation, the Brat-Ket-Dirac notation, works in the case of these density states or mixed states. And simply here we're rewriting everything we've already figured out and known, just in terms of these density operators. So coming back to qubit 1, prepared in the ground state, we're now going to generalize our noise if you remember the coherent noise picture, to say that any gate, such as U1, is preceded by a noise channel, something that does an operation to the quantum state. Now, unlike the previous case where that operation had necessarily to be a coherent state, in this part of our picture, in this toy model, we're going to look at incoherent operations, operations that are no longer unitaries, that are going to act no longer on pure states, but on, well, they could act in pure states, but they will turn them into mixtures of states. So how does this work? Let's look at a toy model of how we can write and think about this particular noise channel. So imagine, for simplicity, that our toy model has a simple single gate. That's the identity gate. So I'll write that as I. We don't want to do anything crazy yet. Let's keep that target gate as the identity. For the noise, let's say that its effect is to randomly cause a bit flip error. In other words, on an individual circuit realization with probability P, a bit flip error occurs, which will express here, due to the noise by the way, which will express here as the random application of an X gate that occurs with probability P. So each time I run this experiment, I either apply the X gate with probability P or with the complementary probability 1 minus P. We do nothing. The noise doesn't do anything. We just apply the identity gate. By the way, this kind of description of a noise is called a quantum trajectory, or a trajectory unraveling. Excellent. Okay, so notice that unlike unitary evolution, we now have something else. We have a probabilistic mixture of different possible quantum states. Remember that in this case, we start with 0, or if you want rho 0 is 0, 0. And over here, we end up with, again, the state 0. So over here, the state, let's call it rho 1 is equal to 0, 0. On the other hand, down here, we start with the state 0, subject to x, that will get flipped to 1. So rho 0, let's call it prime, is equal to 0, 0, but after the application of this gate, rho 1, let's call it prime, is equal to not 0, 0 anymore, but now is equal to 1, 1. In other words, if we now had to write the final state of this entire ensemble, we could say that the total mixed state is equal to the probability of the first event times the state of the first event, let's call it rho 1, plus p1 times, p, there's no 1 here anymore, just p times rho 1 prime, which in this case is equal to 1 minus p 0, 0, plus p times 1, 1. Or, instead of writing 1, 1 and 0, 0, we could have written, let's continue down here under the noise, we could have written this as 1 minus p, the identity applied on 0, 0, which was the input state, times the identity, plus p x 0, 0 x. So notice that unlike the previous operations, we now have a linear combination of different states that are that are convexly combined. In other words, they're summed by weights given by probabilities. So how can we write down the total change in the quantum state, which is now denoted by rho and rho prime? Well, we write this as a noise channel. We can call it lambda or n or any other typically calligraphic letter or uppercase Greek letter, to describe how the initial state, rho, will change into a final state that's mixed, lambda. And notice that the first block of this piece is going to entirely symbolize our first block here, and the second block and piece here will symbolize the second block and trajectory here. So really we've just added two different random or stochastic quantum trajectories and combine them into an ensemble. Let's work out what happens to the quantum state in the following case, that we have bit flip noise under the identity. So to remember to remind us what happens, we have an initial state, rho 0, that starts here, which is just 0, 0. If you take the expectation value on this state for the x, y, and z quadratures, you will get that x is 0, y is 0, and z is 1. How do I know that, by the way? Notice that rho 0, you can rewrite this here. Let's do it below here. You can write that rho 0 is just a 0, 0, which of course is 1, 0, 0, 0. Or I can equivalently write that as the identity plus the z term divided by 2. The expectation value of any of the polys, such as x, y, or x or y, and so on. Actually, hold on. Let's do it a little bit differently. Let's say that the expectation value of x, for instance, is equal to the trace of x times the state rho 0, which is then equal to the trace of 1/2 x I plus z, which is then equal to 1/2 the trace of x plus x times z. The reason I've written it like this is because if you remember, the trace of x is equal to the trace of y is equal to the trace of z is equal to 0. The only poly that has a non-zero trace is the identity, and its trace is 2. So the above expression, if I continue, the expectation value of x, which is 1/2 the trace of x plus the trace of x times z, is going to be 0, because that's clearly 0. X times z is proportional to y, but it doesn't even matter what the prefactor is, because that's going to be 0 as well. And so that gives us 0. Similarly, for y, we have the exact same argument, and for z, we have a similar argument, except that we now have the trace of z applied on rho 0, which is going to be 1/2 the trace of z plus z times z, which is going to equal 1/2 the trace of z plus the trace of the identity, which gives us a 0 for the first term and gives us a 2 for the second term. So this is 2/2 is 1. And so we find that the only non-zero poly here is the z term. You might ask, well, that's very nice. So good. What does that actually look like if we come to it in terms of an actual Bloch sphere or Bloch vector? Well, if you want, we can draw it a bit like this. You can say that this is the Bloch sphere, and this state points precisely in the north pole. That's the 0 state, or the z equals +1 state. Excellent. Okay. So the state after is more interesting. What happens once we have passed this channel? Let's call it rho prime, for lack of a better nomenclature at the moment. Or let's just call it rho, in fact, because there's only one rho afterwards. That's the rho that we will measure. But we notice that this is now the sum of two cases. And I can write it, if you want, this way first, as 1 minus p I acted on 0, 0, I plus p, where we then act with the x state on rho and again on x, which you can see in terms of matrices is just 1 minus p 0, 0 plus p 1, 1, which is a matrix, looks like 1 minus p, p. It's a diagonal matrix with trace equal to 1. The sum of the terms is equal to 1. You might ask, that's very nice, because it tells us that the expectation value of the identity is 1, which is what you would expect. Notice that the trace of rho squared, known as the purity, is going to give us a non-zero value, because that will be essentially the trace of 1 minus p squared plus p squared. So it's 1 minus p squared plus p squared. And that's going to equal 1 minus 2p plus p squared plus p squared, which will then turn into 1 minus 2p plus 2p squared, which you can simplify a bit if you want as 1 plus 2 times p, 2 times p times p minus 1, which you notice is equal to 1 if p is equal to 0. Excellent. Great. Okay, so that tells us that a pure state should have no bit flip errors. Okay. Now we can ask the same question, which is, for this new density matrix, what are the x, y, and z expectation values, which will tell us where on the Bloch sphere this particular state lies? So we can ask, what's the expectation value of x, y, and z? Okay. You'll notice that the expectation values of x and y have to be 0 by the same argument as before, because this density matrix here, which we can write like this, is just the sum of some coefficient on the identity poly plus some coefficient on the z poly. Try to figure out what these coefficients are. I bet you can solve them. So the only term that's non-zero is the z value, and let's work it out explicitly. So this is equal to the trace of z times 1 minus p 0, 0. And if we write this out, we can have then that this is the trace of 1, 0, 0, minus 1 times the diagonal matrix 1 minus p 0, 0, which then is equal to the trace of, and we only need to calculate the diagonal elements since those are the only ones that will actually account for something in the trace. So row column, so we have 1 minus p, and then row in A times column in B is 1 minus p. And so this is going to be the sum of the diagonal, which is 1 minus 2p. So notice what's happening. It means that for it means that the z value as a function of p, let's see if we can draw this. This is p here, and p is a probability, so it goes between 0 and 1 and no further. It tells us that for p0 the z value is equal to 1, and as p goes to a probability of 1, the z value goes to minus 1. And in fact, if I go back to up here, you'll notice that there's actually two values when the trace is equal, trace of rho squared is 1, which means that it's a pure state. And that is precisely if the probability is of a bit flip is exactly 0 or exactly 1, which tells us that deterministically the bit is either not flipped in the first case, or deterministically it is flipped. So while there is an error, it's a completely deterministic error. So no information has been lost, there's no randomness injected into the system, the entropy hasn't increased, and so we still have a pure state, we still have trace of rho squared as 1. And of course, anything in the middle will completely flip the state. Great. Okay, so let's picture that on our Bloch sphere picture. So if I return up here, on the right-hand side here, instead of having a state that goes all the way to z equals plus 1, we're now going to have the state rho be slightly reduced in length, still pointing in the same direction in this case. However, the reduction here, the length of the state, is no longer 1. We used to have a state of length 1. Now our state has a length of only 1 minus 2p, where p is the probability of an error. So the effect visually on the Bloch sphere of this noise channel is to reduce, to shrink the Bloch vector. In other words, it's a contraction on the Bloch vector. You can ask yourself, well, what will happen if I now take this and I repeat it many times, or if I do it for different initial states? I'm going to let you work that out, and if you want to find the answers, they will be in the bonus section of this lecture. But we're just going to jump ahead and visually explain what you expect to see. Let's look at our picture again. Remember that initially the state was 0, and so we found that for our case the Bloch vector was exactly at the North Pole. But let's visualize every possible state on the Bloch sphere, which is precisely what this unit sphere picture is supposed to represent. It's just the unit ball. What happens after the channel? We saw that after the channel, the length here had shrunk by about a factor of 1 minus 2p, where p is the probability of a bit flip error. Notice that the bit flip cannot do anything to a state that's along the x component, right? Because if our state was along plus x, remember that x applied to the state plus, which is precisely what that state here is supposed to represent, as opposed to 0, which is up here. X acted, oops, that's supposed to be a plus, excuse me. X acted on the plus state is going to just give you plus 1, the plus state, again, plus state, and x. In other words, it's plus 1. In other words, it's an eigenstate. So the noise in this case does not affect that particular component. So it's not a symmetric noise, it's a biased noise process. But every other state that is not an eigenstate of this particular noise channel will be subjected to the noise and will decohere. The way that presents itself visually in the Bloch sphere picture is a contraction. So that's why you see the contraction that is small near the x equator, but large at the y equator, and also maximal at the y and z points. So that is the way that we can visually identify the loss of information, the reduction of purity, and we can understand that this channel has a particular effect that causes the loss of information to be pretty strong in this case. You can play with different noise channels like this. So for instance, so far we looked at what happens in this case where we have a bit flip based on the x gate. We can also have a phase flip, a phase noise, where with some probability p we flip the z component. Essentially everything looks the same. All you've done is permuted some of the letters x, y, and z. You can add more general cases. Suppose that there isn't just two choices, but the error could be an x error, a y error, or z error with equal probability, and with some probability 3p over 4, there's just no error. That's a symmetric noise channel that is going to equally decohere the x, y, and z components of your Bloch vector. And we call that a depolarizing noise channel. This is a very, very common, typical assumption in all of quantum information theory, to use this kind of noise channel to model generic noise process. It's overly symmetric, it's not very realistic. A slightly more realistic noise model is that of a stochastic polynoise, which is almost the same as a depolarizing. It's just that it has potentially different coefficients along the different axes of the noise, such as x, y, and z. And so here I've pictured a stochastic polynoise channel where the x loss is 10%, the y loss is 20%, and the z loss is 40%. And you notice that it creates this kind of asymmetric picture. The surface here shaded in dark gray shows us how the pure state unit surface has shrunk under the application of noise, and these are now all the states that one can possibly get after the application of the noise channel. Great. Okay, so let's take all of these different possible noises, and I challenge you to try to work out what each of them does to the density matrix. So you can repeat the same exercise we did, or you can jump over to the bonus section and some of it is worked out there. Let's take the simplest case of the bit flip noise and add it into what happens with our potential with our early experiment that we saw earlier in the data. And here it is. Okay, so what I've done is I've taken the coherent noise, I've added projection noise as well as readout error noise, which we saw earlier. So everything you saw in the previous chapter. And now additionally to that evolution, I've added in at each step this particular bit flip noise with some incoherent probability error of about 1.2%, so pretty small. And notice what it has done. It has caused that oscillation that we previously saw to diminish. So we're seeing this exponential decay. And this should remind us very much of all of the elements of noise. So the incoherent noise here is going to cause this kind of exponential envelope decay. And you notice that the purity of the state, the trace of rho squared, is going to, will always be less than or equal to 1 and greater than 0, and it's going to increasingly diminish starting from the beginning to moving towards the end. And because essentially by the end you've had 100 flips, you've had 100 random bit flips of 0 or 1, by that time you're totally scrambled, no matter, even if your probability is only about 1% per bit flip. So incoherent noise is very characteristic, it's very ubiquitous, you can't really get away from it. It looks typically like this, where it will cause an oftentimes exponential decay, or if you're repeating a circuit and trying to amplify the noise. And it's a typical signature to see that it will tend to bias your result or tend to shift it to one narrow particular range and region. With that, folks, we have come around full circle. We have pretty much reproduced the noisy data that we saw. The only thing we hadn't explicitly added, which is in the bonus section, is just why this curve looks has so many more fluctuations, and that's due to the state preparation and more measurement error. But overall, we covered the projection noise, which causes these fluctuations on the curve. We also covered the incoherent noise in the last chapter, which causes the overall exponential decay of this curve because you're amplifying the noise the more times you repeat the sequence. We saw how coherent noise causes this oscillatory behavior in this case of the function, and how spam noise, or in particular the measurement noise, as well as state preparation, can cause these deviations from the ideal expected values of +1 and -1, even when no particular gate was applied. With that, we've covered the road on your first journey ahead, from coherent noise to measurement, spam, and incoherent. These noises come in a ubiquitous way, and they always come pretty much in every device you're going to use. They're always going to, all of them will always be there at different strengths. Some of them you can sometimes ignore depending on your protocol. You can really dive into the bonus content if you want to understand a little bit deeper what it is. I'd here like to spend just about a minute on the outlook of how do you tackle noise? What about no noise? In particular, if you have some general quantum algorithm and you have some unitary that you'd like to apply, which unavoidably has linked to it some noise profile, let's call it lambda. Is it possible to learn that noise, to understand it? Is it possible to correct that noise with some accuracy, efficiency, and scalability? And keep in mind that this is not an easy thing, because these are real big physical practical devices. We can aim to do this, but remember this is a picture of an IBM quantum chip, that this chip suffers from all kinds of noise sources. There's energy relaxation of the qubits, there's the phasing, there's coherent error, there's classical crosstalk, quantum crosstalk, state preparation, and measurement errors. The measurement errors can even be correlated, so they're not just local, they can be non-local. There's control errors, photon shot noise, 1 over f charge noise, flux noise, non-equilibrium quasi-packet, leakage, cosmic rays, so and so on. Many things that we haven't necessarily talked about, although all of them will render themselves in some fashion and form of that we can describe using the theory that we have so far covered. So all of these different potential noise sources we can describe using what you have already learned, but how do we go about mitigating them and learning them? Well, there are generally two broad strategies. The first part is, let's call it error mitigation. It's working with what you have. It says, I have a quantum processor. I'm not going to change the hardware. I'm just going to try to get the most out of it that I can. And to do that, I have to pay a price. Typically, that price is not in quantum price, so you're not going to use extra qubits, no overhead. You're going to use more classical post-processing. Maybe you need to run more experiments. But using these techniques, which we touched on in the bonus section of the A matrix and how the A matrix can be inverted and calibrated, you can actually undo some of the noise. You can suppress it using classical post-processing, and you can reduce the error, the bias, as well as you can have higher accuracy. So that's really great, and it works quite well, and we're very excited about it. Some recent work that I've been working on as well. The limitation is that it doesn't scale well. It's really just for noisy, near-term devices. It requires a huge number of samples and circuits typically. So it's great for some things, but it's not a silver bullet. What is, in fact, kind of a silver bullet in that it can suppress and correct errors to arbitrarily small levels is quantum error correction, which can actually protect the quantum information as opposed to just doing classical post-processing. However, it comes at a very high cost of large number of qubit and hardware overhead, as well as potentially a large classical overhead in decoding and encoding errors. Not necessarily, but oftentimes these are costly. So it's a challenge because it requires a lot of hardware, a lot of overhead. It requires also fault-tolerant operations and readout, and many other things. It's something that the whole community is working towards. But while we're getting there, you can still get very far and get quite a lot out of quantum error mitigation. To learn more about both of these, I suggest you check out our Qiskit Quantum Seminar YouTube series. Those are ways to learn more. That's a to-do you can check out. We have many of the latest seminar speakers, so that's a good way to really leap into the latest on research side and see where the field is headed. And you'll see me there as your host every Friday at noon Eastern Time. So with that, folks, I'm really happy to have been your guide today. I think the next step for you is to follow up on lab work with Qiskit and run real experiments on the devices. If you want to dig deeper, check out the references and problems given in the lecture, The Dangerous Bends. Remember, this is not the end of your journey. Stay in touch. I'm happy to stay in touch, and I'll try to post some of the answers. Feel free to bug me about them on social media. Try to post them on my blog or somewhere else. And I'd like to always end with a favorite quote that I like to remind myself and folks like you along, from the great physicist Albert Einstein, that the important thing in your journey here is not to stop questioning. What you saw today is not the end, it's the beginning. Have curiosity, nurture it. Curiosity has its own reasons for existence. One cannot help but be in awe when we contemplate the mysteries of the eternal physics, life, and as well the marvelous structure of reality. And we saw that debate between Bohr and Schrödinger vehemently opposed at antipodal points of view on the nature of measurement and the nature of reality. And yet we can very much use that in our quantum devices today. So there are many mysteries we haven't exposed yet. I'm sure you will get to. It's not enough, but I think it's enough if we just get one new small insight, one new lesson we learn, one new thing we comprehend, a little bit of that mystery each day. So if you got one thing, one little mystery out of this lecture, I would count that a success for you and for me. Thank you, and good luck.